Okay, here again I need to find turning points and obviously also their nature, and I need to find points of inflection on this curve, and then I need to sketch it. Now remember, we've got two methods of finding the nature of our turning points. Once we've found our flat spots, we can look at the gradient on either side and see if it's going up or going down. But we can now also just look at the second derivative and see if it's greater than 0, smiley face, or less than 0, frowny face. Okay, so we're going to need the first and the second derivative here, so it makes sense to go ahead and figure out both of them. So differentiating one term at a time, I've got 5x to the power of 4 minus 20x cubed, and differentiating again, bring the 4 down, we have 20x to the power of 3 minus 60x squared. Now we've seen already that it can be handy to factorise these so that when you let them equal 0, you can easily see what the zeros of these functions are. Now remember, we're letting this first derivative equal 0 to find where the flat spots are, and then we're going to let the second derivative equal 0 to look for points of inflection, and we're also going to sub in our flat spots, their x values, to see what the second derivative is doing there. So let's go ahead and factorise both of these. The first one, we can take 5x cubed out the front, and that leaves us with x minus 4. And for the second one, we can bring 20x squared out the front, and that will leave us with x minus 3. So if we let f dash x equal 0, and it's handy just to write this down so you're keeping it really straight what it is you're doing, we'll find the stationary points, won't we? The places where the gradient is 0, the flat spots. So what we're saying is that 5x cubed times x minus 4 is going to need to equal 0. Now when we've multiplied two things together and got 0, one of them must have been 0. So either x is 0 for this part, or x is 4 for this part to be 0. Okay, this gives us the x values where the flat spots lie, but it doesn't actually give us the coordinate points, and we want to go ahead and graph them, don't we? So it makes sense now to say, well, when x equals 0 or 4, what's y? Now, make sure you sub it into the right function. We want to go all the way back to the function we were given in the question. Now, subbing in 0, 0 and 0 here, we're going to get 0. So that gives us the coordinate point 0, 0, and it tells us that's a flat spot. So not only can we put a dot, we can actually put a little mini flat spot there to remind us what we're doing. When we sub in x equals 4, you might want your calculator here, because this is a pretty big number, 4 to the power of 5. That gives us 1,024 minus 5 lots of 4 to the power of 4, and that gives us 1,280. So 1024 minus 1,280, we end up with minus 256. So we've got this point 4 minus 256 to graph as our other flat spot. Now you can make your x-axis have whatever value, whatever scale you like. If we have 4 over here, and just pick the lowest part that fits onto your page, let's call that minus 256. That way you can line your spots up, label that. It's not just a dot, it's a little mini flat spot, and we can label it straight away so that that's done and we don't forget to do it later. All right, find the turning points. Yep, we've found them. All right, we need to find their nature now. Then we need to look for the points of inflection. So to find their nature, we want to see what the second derivative is doing at both of these spots when x is 0 and x is 4. So we need to find f double dash 0 and f double dash 4. Now, subbing 0 in to f double dash x, we're going to get 0. Now, this tells us it's a possible point of inflection. So it's not only a flat spot, it might be a horizontal point of inflection there. We can't tell for sure, because remember, this is that strange rule that says if f dash x equals 0, it might be a point of inflection. But if it really is a point of inflection, f double dash will equal 0. So at this point, we're not sure. We're going to have to do a table of concavities to check. For the other one, subbing 4 in here, we've got 4 4s are 16, times 20 is 320, times 1. So that gives us 320. Now, a positive second derivative tells us that we are concave up. Put a little smiley face there to remind you. So that means this point down here is a little mini smiley face, and we can make it like that. It's a minimum turning point, the bottom of a trough. All right, now we need our table of slopes so that we can investigate whether this really is a horizontal point of inflection or not. Now we're investigating x equals 0, so we'll need to know a point on either side. We can choose 1 and minus 1 here. And we want to investigate what the concavity is doing on either side. So we want to find f double dash x. We already know it's 0 when x is 0, but subbing in minus 1 here, we've got 20 times 1 will be 20 multiplied by minus 4, we're going to get minus 80. Now minus 80 is a negative number. That tells us that we are concave down on this side of the 0. Investigating the other side, when x is 1, we've still got 20, but we've got 20 times minus 2, which is minus 40, and now that's also negative. So we've got concave down on both sides. So this looked like it might be a point of inflection, but further investigation showed us that it actually wasn't. And we need to now draw our curve in, making sure it looks like it's concave down on both sides. How do you do that? Well, if it's concave down here, right at the point, then it's going to be concave down on both sides as well. Now we can draw this in, connecting it up to the other point down there. And this is actually just a maximum turning point. You're going to find this quite often, that a maximum turning point or a minimum turning point, it has f dash x equaling 0, but occasionally f double dash x equals 0 as well. And it most often happens when you've got high powers of x in your function. All right, now we've got two more things to do. We need to find any possible points of inflection. And we also need to find where this x-intercept is here, because it looks like it's going to go shooting up, and we want to get this right. Let's look for this one first. So we want to let f of x equal 0, or let y equal 0 really, don't we, to find x-intercepts. So go all the way back to your original function and say x to the power of 5 minus 5x to the power of 4 has to equal 0. Now don't be tempted to add this term to both sides to get the x's on both sides and then divide by x to the power of 4. You lose solutions. We always want to factorise and multiply two things together to make 0 using the null factor theorem. So instead, factorise it, and then we say if this times this is 0, one of the two things must have been 0, and so x must have been 0 or 5. Now, we've already found this intercept here at 0, so that's telling us something that we already knew, but it's nice to sort of confirm it. And this other intercept must be 5, so 4's here at our low point. By the time it gets to 5, it's already gone shooting up and through there, so I can draw it in like that. Maybe you have it without that wobble there, so it comes in. It must be pretty sharp now at the bottom here. Now, our last thing is to find the points of inflection. There'll only be one. We can tell because we're concave down here and concave up there. So somewhere around about here, we're changing concavity. Now, we need to let the second derivative equal 0 to find it. That means we're letting 20x squared x minus 3 equals 0. And that happens when x is 0 or 3. Now, we already saw what happened when x was 0. It was a possible point of inflection, but it didn't turn out to be one. So this one must be our actual point of inflection, and it happens when x equals 3. So you can label that spot down there. Now, we've got the 3, but we need the y value that goes with 3. So sub that back up into your original function, and you'll find that we've got our turning point at 3 minus 162.